Okay. All right. I'm not sure if the remaining homework 4s have been graded yet. I checked yesterday, and they were still working on the 4.1.4.2. But given that we don't have any homeworks due or any more homeworks that are going to be submitted this week, I'm guessing that by next week everything will be caught up. So let's go ahead and begin. Attendance grades are up to date, up through today. I'm going to also, and I do this for exams, I tend to just count everybody present since I generally know you're going to be here to take your exam. So won't worry about taking attendance on Friday. But with that, I want to make sure that today's lecture is as useful as possible for you because this is really your time to ask questions. So I'm going to pull up the exam review slides. Did everybody get the code? All right, so let's get into the exam review. Let me pull this up here. Okay, so like last time, I have a presentation for you on the review, and it's basically split into 3 things. I'm going to go through first off the logistics on the exam. What's it going to look like? What's the approved materials, etc. No real different than last time. And then the second part, I'll talk about specifically what is on the exam. And then third is sort of my greatest hits of the slides over the past few lectures that has all the sort of, I would say 90% of all the formulas and equations that you would need. Okay, so it's not going to be on Blackboard. It's going to, I don't know if you still have professors that are maybe administering exams through Blackboard, but it's going to be in here, in person. It's not intended to be time critical. I don't really think time sensitivity was too big of a problem on the last exam. And I don't really think it's going to be on this one. But the format is exactly the same. A few short answer questions, and then a few computational problems. It's closed book, closed notes. You are allowed a formula sheet. I do say bringing a straight edge might help. I'll say this, probably not the biggest deal on this exam, but I will say on exam 3 and exam 4, straight edges will definitely help. So I would definitely make sure and bring them, like a ruler or something like that. The same rules on the formula sheets. I have a note here, and this doesn't really apply to this exam, but it definitely will apply to exam 3. We just finished a lecture that's related to exam 3 on centroids. And when we start actually getting back into centroids, we're going to need a lot of references in the textbook, like the centroid of a triangle and the centroid of a semicircle and all of that. Those types of necessary properties for those later exams I will give you. I'm not going to have you waste time on your formula sheet with that. That doesn't really apply to exam 2, but I put that on here just because I kind of wanted to throw that out there while it was on my mind. But yeah, you can put whatever you want on the formula sheet, again, except for fully worked out example problems. And again, I talked to you last time about how that's not really for my benefit, that's for yours, because if you're doing a problem on the exam, and you have a similar example problem on your formula sheet, sometimes you'll have a tendency to take those numbers from that example problem and throw them into your exam, and then suddenly things don't make any sense. So that's for your benefit, not really for mine. And finally, it does need to be prepared by you. I am okay if you snip a formula here and there, if you want to word process it, if you want to handwrite, I mean, whatever works for you. But what I don't want to see is just, here's some screenshots of some slides, hit print. I want you to actually make the formula sheet. I found that students that make the formula sheet and actually take the time to do it end up doing better on the exam as a whole. Okay, let's talk about the topics on the exam, and I believe I have this just on this slide. This is everything that's on the exam, okay? So first off, make sure that you are able to compute cross products and dot products, and that you understand, the associated, I guess, definitions and theories associated with them. But really, the star of the show on this exam are moments, okay? So make sure that you can compute moments. So, in 2D or 3D, that can either take the form of the cross product, R cross F, or it can take the form of M equals FD, F being the magnitude of the force and D being the moment arm, the shortest distance from the point in question to the line of action of the force, okay? Now, there's not just moments about a point, there's also moments about an arbitrary axis where you'll take the cross product and dot it with lambda, lambda being a unit vector along the axis in question. And in this case, R starts at the axis in question and ends on the line of action of the force. Make sure that you can resolve force couples. So take a bunch of couples and resolve them into a single vector. And make sure that you can generate equivalent force systems in 2D or 3D. Take a bunch of forces and change them into a single force in a single moment, or a single force at a given point. So that's everything with rigid body systems. And with rigid body equilibrium, what we're talking about there are support reactions. Make sure that you can compute support reactions in 2D and 3D. Now, I said this on Monday, and I will say it again. I'm not going to say that 3D has been eliminated from the exam, because it's not. There are some 3D problems or 3D components on the exams, but I have minimized the amount of 3D as much as possible, simply because I know 3D takes a lot of time, okay? And I don't want this to be a time crunch. I have done this exam myself. It took me about 15 minutes to do it, so you should be able to do it in 50 minutes with no issue. All right. The rest of this presentation are just formulas, okay? So first off, there's the cross product of two vectors. So remember, we're defining the cross product such that the magnitude equals the area of the parallelogram formed by the two vectors, and the direction is normal to the plane that that parallelogram occupies. The way that we compute that is we take the determinant of this 3x3 matrix, and there's two ways of doing it. We can either use the rule of Saris, where we take all our products this way and treat them as positive, take all our products this way and treat them as negative, and just sum all that up. Or we can use cofactor expansion. I actually kind of prefer cofactor expansion. I think that while there are, I guess I should say, you have to be careful with managing your signs, I think in the end it's easier to collect all of your terms. And then these 2x2 determinants, you just do that times that minus that times that. That's the cross product. Dot product's pretty simple. So if cross products yield vectors, dot products yield scalars. So really all we need to worry about is the magnitude. And the magnitude is ultimately the magnitude of each of these vectors, the product of those with the cosine of the angle. If the cross product was defined as the magnitude of those two vectors times the sine of that angle, will give you the magnitude of the cross product. That's why we use cosine here. So we get a somewhat unique response. And in order to compute the dot product, it's really easy. You just multiply each of your like terms and add them. Pretty straightforward. We have our formal definition of a moment. So we formally define the moment about a point in question as r cross f, f being the force vector that you're looking at, and then r is a position vector that starts at the point in question and points anywhere along the line of action of that force. Okay? It doesn't matter what r value or r vector you use. If it starts at the point in question and points on the line of action, you will get the same moment vector every time. The magnitude of that vector, so if you had a 3D vector, you could compute the magnitude with the Pythagorean theorem like you would any vector, but you can also set that equal to FD. F being the magnitude of the force in question, and D being the moment arm, the distance from the point in question to the line of action. So you can use cross products and whatnot to determine moment arms. That's another sort of roundabout way of doing it. For moments in 2 dimensions, what happens is we use cofactor expansion. We recognize that if we're dealing with forces and moments in 2D, that if we say our z terms go to 0, then we end up only having a single vector or a vector with a single component along the z-axis or associated with the k vector. So a lot of times for moments in 2D, we dispense with the vector notation altogether and just deal with the scalar component, rxfy minus ryfx. If we're computing moments about an arbitrary axis, all we're doing is, instead of I, j, k here, we just use the x, y, and z components of the unit vector along that axis in question, okay? So remember, r is the force vector, f is the force vector, r is the position vector. But with this time, it ends anywhere along the line of action of f, but instead of starting at a given point, that's a typo there. Instead of starting at a given point, it starts along it starts along the axis. That's a typo. I'll fix that later. All right, force couples. If two forces have the same magnitude, have parallel lines of action, and point in opposite directions, separated by some distance, they form a couple. Okay. So you can still use r cross f R starts on the line of action of one force and ends along the line of action of the other. And so that computation should be relatively straightforward. Really, the star of the show with that first unit of the class was equivalent systems. The idea that we have a system of forces and we can transform that into another system by summing up all the forces and summing up all the moments. And those two systems are said to be equivalent if the sum of forces in system 1 and the sum of moments in system 1 equals the sum of forces and sum of moments in system 2. And so it's a good way of taking a lot of forces and cramming it into a more manageable set. For static equilibrium in 2D, we have 3 equations of equilibrium that we need to satisfy: sum of forces in the x direction, sum of forces in the y direction, and sum of moments. In 3 dimensions, we have 6 equations of equilibrium, but again, given that this is a time-sensitive exam, if you have a 3D problem like this, it's definitely going to be very abridged, and it's not going to be a full deal problem like in homework 4.3, for example. For the support conditions, I'll go ahead and tell you, I'm not going to get crazy with it. It's going to be pinned, roller, and fixed, like nothing beyond that. I'm not going to use any of these weird, collars on frictionless rods or anything like that. I'm not going to do that. I don't think that makes the concept computationally more difficult. I think that just for the purposes of an exam trying to assess you on the understanding of the concept, I think it just adds more than really is necessary. So, and I think in the real world, a lot of stuff like that, you're either going to handle with more refined methods like you might learn in a kinematics and design of machines course, or you're going to surrender to a little bit of software and let it handle it for you anyways. So here's our static equilibrium conditions in 2D. Here's our equations in 3D. And that's it. That's basically the contents of what's going to be covered on exam 2. So again, to be crystal clear, nothing about centroids on exam 2. Okay. Now, some of this material that we had in exam 1 does kind of bleed over a little bit. I mean, like for example, you are adding forces and whatnot. But again, the star of the show is moments in 2D and 3D. All right, with that, I'm going to shut up, and I'm going to say now it is your turn to ask questions to me. Yes, sir?
Is that going to be pushed to Blackboard?
It is. Should be there now. Is it not there?
I don't see it either. Yeah, I don't see it.
Yes, it should. So I think it's there, but it might not be visible. I'll turn it visible. I'll fix that. So I'm sorry about that. Yeah, absolutely. I won't deprive. I'll tell you what I will do. Not only will I do that, I'll just turn everything on for the rest of the semester. Because I actually have every lecture note for the entire semester on Blackboard. I thought I had already turned them on, but whoops. I must have missed one. I'm sorry. But yes, absolutely, I'll make these available to you. And there was a typo on the one slide. I'll fix that. Yes, sir?
Is there going to be any of those pulley problems where you got to cut a section?
Any pulley problems? There won't be pulley problems. That was totally an exam 1 concept. The first 3 exams in this class are not comprehensive. That doesn't mean that there aren't like forces on the exam. I mean, of course, there's going to be forces, but I'm not going to examine you on things like particle statics or pulley problems or anything like that. Yeah, that's not worrying about that. Stuff like that may show up on the final though, because the final is comprehensive. Yes.
So when you said if we're doing the static equilibrium in 3D, it would be an abridged version. So by that, do you mean that like you had specified like what sum of forces in a direction we need in the sum of moments?
That's a good question. So that's a possibility. Another possibility is that I give you a bunch of the vectors. Because I think maybe you disagree with me, but for me, I think that when you're doing a 3D equilibrium problem, most of the work is not actually 3D equilibrium. It's coming up with all the damn vectors. Like if you have a force, it's like, okay, let's do the distance vector, and then let's divide by the unit or the magnitude, and then let's multiply by the magnitude of the force to get the force vector. That takes time, right? Whereas if I just gave you the force vector, would it really matter? Like, would it really change the overall process? Like, by now, I think you all are good at that stuff. I mean, we had all that stuff on exam 1. I've given you so many homework assignments with that I think we beat it into the ground. So stuff like that, I may give you vectors to make your life a little easier. And I might do that on other problems as well, where there's a problem, and instead of having to come up with it all from scratch, I'll say, oh, by the way, here's the position vector, or oh, by the way, here's the lambda vector, so that you're not having to do all of it. You only have to do some of it. So that does lead to another point. I would make sure that you are reading the problems fully before you're doing it. Like, take a second and look at what all I'm giving you. I have seen, there was a problem I gave 2 years ago on this exam, and it was exam 1 2 years ago. And the only thing that you had to do on the problem was I gave you a 3D problem, and I said, just give me this vector. That was it. But there were a lot of students that took it and tried to do a 3D equilibrium problem with it, and it took forever, and the problem was only worth like 5 points. It's like, don't do that. Like, just read, just what happened was everything they were doing was right, but then they didn't have any time to do the other problems on the exam, and they sort of screwed themselves over. So, I would just really reiterate, make sure you're reading the problem. Because I'm really trying to not make this a time crunch. I don't want this to be a time crunch. And I'm doing my best not to have a bunch of repetitive calculations over and over again. I like it when each problem is unique, that we're not doing the same thing over and over again. I assume that answered. Yes?
We did this problem in class one day. It was like a box, like a 3D box, and it had the X, Y, and Z axis, and then like there was an R vector going down the middle.
Okay.
And you had to find RX and RV.
Do you know which problem it was?
It was on 10/5, October 5th.
Let me see. Hold on. Let me see. I might be able to diagnose that. Give me a second. October 5th. So, okay. Equivalent systems in 3D. Okay. You're talking about this one right here? Or this one?
No. It was like RZ was 3 feet and RX was 3.5 feet.
Wait, say that again?
RZ equaled 3 feet and RX was 3.5 feet. That was the answers.
Oh, that's this one. That's this one right here.
Yeah.
Yeah, that's this one right here.
Okay.
Yeah, that was this part. Because, yeah, so what we had to do was the problem had a square mat foundation that had a bunch of loads on it. So we added up all the forces, added up all the moments, and then figured out where to place the force such that, you got the same moments. And yeah, it was 3 feet and 3.5 feet. Yes.
There's going to be one like that on the exam.
Possibly. I'm not saying it's going to be this problem exactly, but possibly. What I will say is that, so let me give you a parallel, okay? So if you go back to this problem, okay, and you'll see where I'm going with this here in a second. So with this problem, we had the barge that had a series of boats that were applying load to it, right? And so this is what I would call system 1, right? So the original system with the barge and the 4 loads on it. And then what we did is we turned this into system 2, okay? System 2 was this, right? So what we do, we took all those forces, we added them up to get a resultant, and then we did R cross F for each of those forces and added those up to get a resultant moment. So system 2 was just a force and a moment. And then system 3 was, okay, let's get rid of that moment and let's only deal with the force. Where do we place that force to generate the same amount of moment? And we got a value of, like X is 41 point some feet. This problem and this problem are exactly the same, just one's in 2D, one's in 3D, right? So it didn't make, from my perspective, I don't think it made it any more conceptually challenging, but it did make it longer because it was 3D. But this is the kind of thing that I'm talking about. So like a good example of what I might do on the exam, just to use this example as an analogy, let's say I gave you this exact problem on the exam, let's just say that. What I might do is give you all the R vectors to make, because that's something that you don't have to do. Or I might give you all the force vectors and all the R vectors. I think I did that actually on a previous example. So this example here, we had to do something very similar, but I went ahead and gave you all the F vectors and the R vectors because just coming up with some of these F and R vectors would just take a lot of time, and I'm really not trying to add that type. I don't want the exam to be littered with busy work. I don't like that. I'm not saying you don't have to do this once or twice, but after a while, it's the same thing over and over again, and I don't like that. But can a problem like this be on the exam? Yes, but it may be in 2D, it may be in 3D. What I will tell you is I'm not going to do both. I'm not going to do a 2D problem and a 3D problem because they're the same thing. It's just a different context. Did that answer your question? Yes.
You know how you have that chart on up there that said like different vectors and moments, like the way it's going to be positioned. Can you tell us which one of those you might put on the test so we know what to focus on?
What?
So it was the last slide of the review.
Oh! You're talking about
Yeah.
You're talking about the boundary conditions. Okay. So here's how I would address that. And maybe I should have put this slide in my review slides, but I didn't. Okay, so let's take static equilibrium in 2D, right? Okay, so these are all the potential boundary conditions that the textbook lists, right? Okay, so in 2D, the only ones, let me find maybe it's this one right here. Oh, give me a second. The only ones that I'm really going to worry about are those. I'm not going to, there are oodles and oodles of other potential iterations as the textbook lists, but I'm not going to do that. I'm just going to use these.
Okay.
And as for in 3 dimensions, the only boundary conditions that I'm going to use are the ones that we've already used, the ball and socket ones, and then like the cables. That's it. I'm not going to make it any more intricate. I don't think that adds any rigor to the concept. I really don't. And while this does not matter at all in this class, from my perspective, what adds intellectual rigor to the concept is making the systems indeterminate, having more unknowns than you do equations of equilibrium. But we're not equipped to solve that in this class anyways, because the only way that you can assess that is to deal with deformation. That's what Engineering 216 is all about, is how you handle deformable bodies. We're not talking about that in here. This is just rigid body mechanics. So you'll handle those problems next semester, is what I'll say. It's fun. I think it is, but then again, I was okay with this class being at 8 o'clock in the morning, so don't trust what I say. My core C valves just drop a little bit. It's your fault that we're here this early. Oh, I know there's got to be more questions than that. How are you feeling about the exam? Are you nervous, relaxed? If you are nervous, what are you nervous about? Because I don't want you to be nervous. I want this, I joke when I say it's a celebration of learning, but I don't want this to be, anything to be stressed about. It's important, but it's not, earth-shattering or anything. Yes?
Do you think going over the homework problems or the lecture problems would be better?
That's a good question. So I would say, here's my best way of answering that. I've tried my best to align the homework problems with the lecture problems. Like I didn't want them to be too far off the mark. But I'm sure that there were a couple of homeworks that were just tough, right, in comparison. I would say, so this is going to be an odd answer. In those instances, I would probably study the homework problems, but I would probably expect lecture type problems on the exam, if that makes any sense. Like that level of rigor or that level of difficulty. I'm not saying that there isn't going to be like like a challenge here and there, because I mean there are some questions on the exam where I am trying to get you to think, but they're not mathematically rigorous, I guess I would say. I'm not going to try, again, I want the exam to be something that you could do in that 50-minute time period very comfortably. I don't want the time to be that much of an issue. But I'll tell you the reason I use that, that explanation: to study the harder problems but be ready for the easier ones. So I assume everybody in here is planning on taking your FE when you get a chance. I'm hoping. If not, take it. You know. But when you get a lot of the study materials that are commercially available, like PPI or Test Masters or stuff like that, what ends up happening are those test materials, they're hard. They're tough. You know. But the idea is, if you can do that, you can damn sure do what's on the exam. You know what I mean? So I would probably kind of use that analogy. Again, I'm not saying the exam isn't going to have some challenges to it, but I'm not trying to overtly trick you. So if you can handle those tougher problems, you can certainly handle what's on the exam. At least that's I feel. Does that answer that? Or no, that was a little long-winded, but I wanted to be clear. Yes.
Are there going to be concept questions on this test too?
Yes, about 4 or 5. But they are short. Like, I mean, so what I'll say is, I have had some exams in the past where I get some Shakespearean sonnets for some answers that go on and on. I'm like, that's a 5-point problem. It is not worth that time. I mean, and I'm not also going to level with you. I'm not a composition professor, an English professor. So here's an example. The first exam, we had a question, and it was, what's the length of I plus j plus k, right? Okay, the answer was the square root of 3. What you don't need to do is say, the length of the vector given in this problem is computed using the Pythagorean theorem and is equal to the square root of 3. Just the square root of 3. You know, I mean, that's okay. You know, you don't need to elaborate. Write what you need to describe your answer and nothing else. Move on. Okay.
Definitions of moments and forces and that kind of thing, or like what kind of concepts does it focus on?
Some of them are, and some of them are. I don't want to use a circular answer, but some of them actually are asking you questions about the concepts. And if you understand the concepts, you should be able to answer the question. So some are definitions, some aren't. So I would love to give you a clearer answer than that, but I'm so starting to broach on just telling you what the question is, and I'm not doing that. So. All right. I will say one thing, if this helps. I cheated maybe ever so slightly on my conceptual questions on the last exam, because one of them required a little bit of math, right? The very last one, because it was the square root of 3. If you want to call that math. None of them do on this exam. None of them do on this one. I ain't saying any more than that, but I'll tell you that. Yeah, there's no real computations required for any of the conceptual questions on this. That doesn't mean that there isn't some reasoning needed. Yes?
Do you have any advice on like how to approach a problem? Like figure out what it is like you need to actually solve for, like when you first read it?
That's a good question. So first off, with this exam, I'm going to try and say this without revealing too much. The way the problems are worded on this exam, it's abundantly clear what's being asked for. It's not like an open-ended problem where it's like you're supposed to, like, what does he mean? Like, you'll know what I mean. To give you an example of something that I'm talking about, maybe related to a math exam. I mean, there might be problems on the exam where I'm like, tell me what X is. You know, like there's no ambiguity. What's X, right? So that's the first thing I would say is read it. Like actually read what it's asking for. I'll say this. One of the problems on the exam, I think, or actually no, 2 of the problems on the exam, I think it will be abundantly clear on how to do it. Like I think so. They are reflective of direct concepts that I've mentioned in the exam review and direct concepts that we've done in class. There's one of them that has a little bit of a challenge to it, a little bit of a quirk to it, but even with that problem, I think you'll know the approach, okay? Because they're following modules that we've done in class, right? So, like, for example, if I give you a problem on reactions, okay, you should know, okay, it's a reactions problem, right? So I have some forces in the x direction, I have some forces in the y direction, some moments, set them equal to 0, and solve, right? It's very procedural, right? If it's a equivalent systems problem, okay, I sum the forces, sum the moments, there's my system with just a force and just a moment, and then my third system is, where do I put that force to generate the same amount of moment, right? You can follow along that linear process. I would say that these problems are much more process-driven than maybe the last exam. I kind of think so. So if to give you a short and sweet answer, match the problem to the equivalent concept we've done in class, and I don't think the process is going to be all that any different. I wish I could give you a better answer than that, but I don't want to reveal too much about what's on the exam. Maybe one other thing I'll say. Take a step back and think about it before you start just jotting stuff down, because sometimes you'll go down the wrong path, and now not only do you have to start over, but you have to start over with less time. So just take a second and think about it. I know it's time, but it's not that time. You can take some time and think about how you're going to do it. I don't think I have a better answer, but maybe if you have a follow-up, I might be able to answer it. Okay. Anybody nervous about the exam? Feeling better? Is anybody feeling better? And if you're nervous, what are you nervous about? Because if there's anything I can do to help allay those concerns, I will try and do it. Believe me. One thing I will say that I kind of like about these classes, or this class, all of the problems do have definitive answers. There's not this open-ended, well, it could be this or it could be that. No, the problems all have a x equals 2, whatever type answer. They're definitive, they're clear, and I think they're pretty easy to identify. So, one other thing I'll say is I think that there's not going to be too much issue with units on the exam. I think that's going to be pretty straightforward. That helps out. Units tends to not be as much of a challenge in this class. In 216, it actually becomes a little bit more of a deal. That and maybe fluids and stuff like that. Any other questions? I can give you 27 minutes of your life back if you'd like. Or we can stay. I mean, I want this to be a valuable exam review experience for you. So, going once, going twice. I'm pulling up the code one more time. We'll see you Friday morning.